Okay, so this is week 11 of Psych 3280, Neural Base of Consciousness, and this week's topic is consciousness and integration. So first, recap of week 10. There, I introduced the theory of consciousness called Integrated Information Theory, or IIT, for consciousness. And logic of this theory is, as the title of the paper says, it is from the phenomenology to the mechanism, and which is a different kind of approach from other types of the theories, such as global neural workspace theory. And what it tries to do is, rather than tackling the hard problem of consciousness from building up from what we know about brain and then to explain how the brain produces consciousness, rather, we first try to identify the properties of the phenomenology, conscious phenomenology, and then to deduce what kind of neural mechanisms can support such properties. And as depicted here, the five fundamental properties IIT identifies is first, intrinsic existence, that consciousness exists, and the composition, that is that in any experience, conscious contents is composed of various components. And then informativeness, meaning that any moment of consciousness is informative in the sense that it excludes, or it's one out of many possible conscious experience. And integration means that the conscious experience is always experienced as a unified whole, not split by this split-like kind of image. And also exclusion means that the consciousness is experienced as at a particular scale with a boundary, and no less, no more, in terms of space and time, as well as the features. And here's the schematic of the IIT-inspired index called perturbational complexity index. So here, what IIT predicted was that the level of consciousness should be high when the brain is in a state of highly differentiated and also integrated. And now this PCI or TMS EEG methodology does is, rather than to gauge the content of conscious or the level of consciousness in the patient by motor response or sensory input processing, directly stimulating the brain and then measure its property, response property. And in the case of wakefulness or REM sleep or locked-in syndrome or minimally conscious states, where multiple measures of consciousness indicates that they are conscious, there the evoked pattern of the neural activity is quite complex. It propagates across many areas, and so it extends over time. However, under the non-REM sleep or anesthesia, general anesthesia or vegetative state wakeful syndrome, the evoked response by the TMS usually dies out really quickly, or it generates a uniform activation, which also dies out really quickly. And the PCI quantifies this complexity of the evoked response in some way, and then it seems to be working as a sort of the most promising measure of level of consciousness. And that's the what we learned, what I explained last week. All right. So in this week, we'll introduce how to compute integrated information. And from the viewpoint of IIT, we will examine the cases of altered states of consciousness, in particular split brain, but also we recap a couple of cases as well. So the learning objectives of this week is to answer the following questions. First, how can we compute integrated information? And how can we estimate the proposed boundary of consciousness? And I'm going to give, again, non-mathematical kind of explanation, and I will not examine this in the exam quiz in detail. But the level of the detail that I explain in the slides is fine to go on. Then the second question is, what are the reported phenomenology or behavior of split brain patients? Then, how does IIT explain various known facts about consciousness, such as split brain patients? The first part of the lecture is about a recap of the IIT first. And as I said in the last week, IIT is a theory of levels and boundary and the contents of consciousness. And you can think of it in this order. The level of consciousness is the system level integrated information. And that's approximated by the PCI, but it's, the real integrated information is not really like that kind of a number, PCI. And I'm going to try to explain this week. And then in terms of boundary of consciousness, it is, I'll come back to this throughout this week, but it is a subset of the mechanisms that maximizes system level integrated information. Okay, if you don't understand it right now, it's fine. And then the contents of consciousness, or qualia, is the pattern of the integrated information among all subsets of the mechanism within this boundary. And this is going to be the topic next week, the final lecture, Frontiers in Consciousness. All right, so the remaining questions from the last week was that now, if you are convinced that, PCI seems to be a good proxy for the level of consciousness, then the next question is that, how we can actually, measure the real integrated information. And if it is a proxy, PCI is a proxy, then if we can develop the method to actually compute integrated information, it could even further, improve the measurement of consciousness and get to the even communication with the non-speakable patients and so on. And then in the course of this measure of integrated information, it's also important to estimate the boundary of consciousness, which of the within the system, which part of the system is generating conscious experience or supporting this, conscious experience that the system is experiencing. And understanding these is definitely necessary to understand IIT's explanations of what we know about consciousness, but also it's important to make a prediction on consciousness into the future. Okay, so then how can we compute integrated information? So to be exact, it is actually best to go into the original paper and the latest version of IIT 3.0, which uses just a simple, mechanism for the explanation, but it is already quite a long tutorial. And if you go to this tutorial video, you will see exactly how it's computed, at least for the very, very simple systems. But this week, I'm going to give a lecture based on this previous version of IIT called IIT 2.0, because this one has a easier way to explain the concepts to the people. And in particular, these 3 papers will be most useful if you are interested in understanding it. But still, the 2 initial papers are quite much heavy. My paper in Philosophy Compass doesn't use much math, so that may be the easiest way to get to that. All right, so the overall idea behind the computation of this quantity called the integrated information, this quantity itself is nothing to do with consciousness. It's similar to any kind of network property of whatever you can find in any textbook actually. So first procedure is to determine all possible states for subsystem can be in. And here, for example, if last week we considered a photodiode, which has 2 states, either on state or off state, and that's like these 2 possible states. And one neuron also we can consider it's either firing or not. But if we start to distinguish different modes of firing or different membrane potential, then there can be many more states for our neuron. And then next step is to determine how much of its future or past states, these subsystem states, are constrained or determined by its current state. And this is what we call intrinsic information. How much of this current states of the system knows or predicts about future past states. And that's what it means that it is intrinsically, from the inside perspective, how much it knows about itself information. Okay, and for example, if the system's behavior is completely random, and the randomness comes from just a pure mechanism of this system, and if the system doesn't have any access to this randomness itself, then it can't predict any future, and so it doesn't know anything about its past state. So that corresponds to no intrinsic information. And then next one is quantifying how much information the subsystem loses when it is minimally cut. And this minimal cut is a very important kind of concept for the integrated information. And the amount of the loss is integrated information. Okay. Let's start with this most simplistic system. So we now consider this hypothetical neuron A and B, which copies its states to the other with a different time step. And this neuron system, you can imagine that it has only 2 states per neuron, so it's either on or off. So A could be on or off, okay, and B could be also on or off. And then AB itself could be on or off on or on off or off off. There are only 4 possible states in this system. Now we consider a simple example of this situation. Let's say when the current situation of this system, current state of the system is on off, neuron A is on and B is off. Then the next time step, because of this copy rule, A's state becomes on off, and then B's state becomes on. Okay, so this is on, and then this becomes on, and then this is B state, A state, and then off state B is copied to A. Okay, and the important thing here is that the system AB future state is completely determined by the current state. There is no ambiguity. And there was previously possibly 4 states, but now it's determined into 1 state. If you know the information theory, it's corresponding to the reduction of the uncertainty. So the next is that you can do the same thing for the past. Now, if the current state is on-off, then it must be the case that the neuron A and B was off-on situation because of this copy state, a copy mechanism. So now, by now, you can kind of already understand that the state of the system, A, B, or anything else, is determined by the mechanistic states of each individual things, and how it transits from one state to the another is determined by how the rule of this connection is. And in the case of the brain, it's likely to be probabilistic, so it's not like deterministic like this. And then also the copy is not like the first most unique or most sort of the probable kind of mechanism in the brain. It's more to do with just adding the output from A to B, and then B receives many other neurons, roughly like 1,000 to 10,000 neurons, and then when B collects all these input over a certain period, and if it exceeds some threshold, B fires. So it's more like sum and then threshold type rule, but I'll just simplify everything here, and it means basically you can identify or define these past state and future state based on the current state of the system. Okay, this is just a simple kind of definition. And then now, how much intrinsic information does A, B jointly together have? So to address this question, what IIT propose is that first determine all possible states what system can be in, and then in our case, our simple example case, it's a 4 states, and then determine how much its future or past state is constraint determined by its current state, and then in our case, it was completely determined. So it's a 2 bits. If you know this, the terminology bits, then that corresponds to 2 units. The state is completely determined by each. So 1 bit plus 1 bit, and that's 2 bit. And that corresponds to logarithm of the 2 states over 4 states. 4 states is now reduced into 1 state. That's the information terminology, okay? But you don't need to understand this part. Now, what happens if we cut the system in the connection between A and B? And cutting operation in IIT can be considered as replacing that wire with a noisy connection. Okay, so if what happens if A, B, and B is instead of copying to each other, replaced by the noisy source of the wire? Like previously, the states of the system remains for on, off. So that doesn't change. What changes is this predictability to the future and knowing about the past. Because of this noise, A tries to copy into B, but it's corrupted. And B's state off is also trying to be copied to A, but it's again corrupted by the noise. And by noise, we define that both on and off happens 50% of the time. Then we just can predict its state at all, A and B at all. Okay, and that's the same for the case for the past state. Even if the system is in an on-off state right now, it could have been that an off-off or on-on or off-on or on-off state that gets corrupted by the noise and then come to the current state. So we have system AB has no knowledge about future or past of its state. It doesn't have any intrinsic information about itself if the connection is replaced by the noise. Okay. So this corresponds to the step of the quantifying how much information it loses when the subsystem is minimally cut. And this is defined as an integrated information. Okay, so just in terms of the equation, like conceptual equation, like format integrated information value, phi, sometimes called phi, is defined as original intrinsic information, how much it knows or constrains future and the past, minus intrinsic information after the cuts. And in this case, we knew about its future and the past 2 bits, but after the cut, we don't know anything about future or past, and that's 0 bits. And subtraction of 2 minus 0 corresponds to 2 bits. 2 bits of integrated information in this system. And then I haven't actually discussed about what is a minimal cut up to now. And this is very important concept, and many people don't understand this in the people who criticize IIT, but I'll just try to go through it. So the key idea here is that to estimate how much a system is integrated, we need to find one way to find the weakest estimate how much a system is integrated. IIT basically proposes to find the weakest link of that system and then cut there to identify the integratedness. Okay, so for example, our example that we used last week, this kind of complicated system which has strong or weak connections, and many of the systems have a bidirectional or unidirectional kind of connection. There, no matter how you try to cut the system, let's say you want to cut only this one, or maybe you want to cut like here, we lose a lot because the state of the next system state based on the current state of the system is influenced and also informed by all these connections. So if we replace some of these, connections by the noise, it will reduce how much the system knows about itself, no matter what, kind of this, connection. And this is a kind of situation where the system is highly integrated. But we need to identify which one is the weakest link to really compute this integrated information of this system. And that's very different from, PCI kind of idea, okay? On the other hand, this kind of system, which we also, propose that the PCI should be very low, here, it's really easy to find out, what's the minimum count, right? So if we cut the system at, let's say, this horizontal line, then there's absolutely nothing we lose about itself's future or itself past, because there is no connection to begin with. So we don't even need to replace it with a random noise connection. And this is a case of the low or zero integration system. However, to conclude this, we need to actually cut carefully, or after identifying the weakest link first. For example, if we cut the system in this diagonal line, then and replace all these cut system with a noise thing, then we do lose some of the intrinsic information. And this is the reason why we need to find the minimum count. And this system's integrated information is always evaluated at the minimum cut or weakest link. And then we move on to come back to this the case of the cerebellum. In the week 3 lecture, if you remember, I introduced this patient who was born without cerebellum, and this is the sagittal view, and this is a coronal view. And this person had some difficulty in the beginning of the life in terms of movement or language, but by the time she became adult, she was very intelligent, and there was no problem, and so on. And then a clinical evaluation of this person ended up in this statement: evaluation of the sensory system showed no abnormalities. And she was just, hospitalized for completely different reasons other than consciousness. And then there she discovered that cerebellum was missing. But at the same time, I also emphasized that cerebellum, as although the small in terms of volume, it contains 4 times more neurons than the cerebral cortex. So it's very puzzling why this is the case. And I didn't give any kind of explanation why it is the case. But now, knowing IIT, we can at least give a principled explanation. So what IIT proposes as an explanation of this no loss of consciousness due to the damage in the cerebellum is that basically cerebellum architecture, if you look at the neuroanatomy and also physiological studies, then they are more or less like, operating in a locally parallel circuits, okay? And then also it is a feed-forward mostly. And feed-forward, receiving the input from prefrontal cortex and basal ganglia, and then to cerebellum, and then feed back into these areas again. So it's a kind of loop, but feed-forward loop. And that controls very careful timing and so on, which is very important for language control or motor control. And if you apply IIT kind of idea, then what happens is that these hugely packed and also densely packed, very large number of the neurons, they are mostly configured like this way, and each of the module may contain some bit of the phi. So maybe we need to define minimum cut here or something like that, but if you consider only this module, then the phi value is possibly 20. But if you consider all of this, cerebellum circuits, then obviously there is a weak link here. And there, it doesn't, you don't lose much because each of them is doing its own thing. So if you cut the cerebellum here, the result of this computation doesn't get affected. And this results in a prediction that cerebellum as a whole, this is a picture, anatomical picture of the cerebellum, as a whole should generate really minimum integrated information. And therefore, it doesn't generate, or it has minimum influence in consciousness, roughly speaking. So summary so far is that, first of all, phenomenological observation wise, I said that IIT starts that our conscious experience is highly intrinsically informative. Each moment of experience is highly distinct and differentiated. Okay, and then to support this type of phenomenological observation, IIT proposes that this intrinsic informativeness has to be supported by some kind of mechanism. That the mechanism has to be intrinsically informative, and that corresponds to this, having lots of states, and also having some kind of knowledge about its future and also past. That's the intrinsically informative system. Okay, so that's the reason why we don't predict that the photodiode is not really unlikely to be conscious, because it doesn't have much repertoire for the future or past. And then the exact algorithm of the IIT is to quantify how much a system constrain its past or future. Second, phenomenological observation-wise, our conscious experience is always integrated and experienced as a unified whole. And that's the sort of second or third actions of IIT. And then IIT's proposal is that to support this nature of this conscious experience, then the physical system that generates conscious experience has to be integrated in some way. And then to quantify the integratedness, the IIT then suggests that we can quantify this by quantifying loss of its intrinsic information by the cut. And the cut at the minimal cut, weakest link. That's the integrated information. All right, then what I finally explained was that the clinical observation of this cerebellum patients. So cerebellum contains 4 times more neurons than the cerebral cortex, but and performs highly sophisticated computation like motor control, language, production, and so on. However, we do not seem to lose consciousness when it's lost, and it's not only because of the birth defects, but also if you have a cancer in the cerebellum, sometimes you need to take it out, but even if you take it out, you do not die or you do not lose consciousness if it's done properly. And the reason that IIT explains is that the cerebellum does not generate integrated information, if anything much. And therefore, it's irrelevant for consciousness, and therefore we can cut that, or it doesn't affect experience. So now the next question is that what is the IIT's proposal about the boundary and the contents of consciousness? And the contents of consciousness next week, and then next part of the video is about the boundary.